thank you, and many thanks to the organizers for the invitation and the opportunity to speak here. It's a pleasure to be here. So yeah, I'm going to talk about indefinite spectral triples. So just like the previous speaker, Nicolas Franco, the main motivation is the idea that we want to study non-commutative space-time as well as just non-commutative space. So we have to somehow be able to switch from Riemannian signature to Lorentzian signature. And if you look at, say, for instance, the canonical example of a Dirac operator on a Lorentzian spin manifold, one of the first things you notice is that this operator is not self-adjoint. So this is one big hurdle to take if you want to move to the Lorentzian case. And this not being self-adjoint is not just because you have a symmetric operator where you chose the wrong boundary conditions, but it's really because you don't have a symmetric operator to start with. So what I'm going to do first is say a few things about how one might deal with symmetric operators, or I mean non-symmetric operators. So consider an operator D, and I assume this is a closed, unbounded, densely defined operator on a Hilbert space H. And the main assumption I'm going to put on this operator is that the intersection of the domain of D with the domain of its adjoint is, the main assumption is that this is dense inside the Hilbert space, but for convenience I'm going to assume that this is a core for the operator D. So given that this is dense, I'm now going to define on that domain a few new operators, namely the real part. So we take the sum of D and its adjoint divided by 2. The imaginary part, minus I on 2 times the difference of D and D star. And then I'm going to define 2 more operators, D plus and D minus, as the sum and the difference of the real and imaginary parts. So all these operators, by assumption, are symmetric, and they're densely defined on this domain, so they are closable, and I will use the same notation for their closures as well. Okay, so next what we're going to do is we can equip this dense subset, domain D star, with a few norms. So first of all, I'm going to define a norm D star, which is basically a combination of the graph norm of D and the graph norm of D star. And we can define similar norms using the real and imaginary parts of D. D. And furthermore, say plus minus, using the plus and the minus. Now, the first observation is that the intersection of domain of D and D star is actually complete in this norm. So we have a Banach space. And you can say a little bit more. Namely, all these 3 norms are equivalent. And using the equivalence of these norms, it follows that domain D intersected domain D star is equal to the intersection of the domains of the closures of the real and imaginary parts. and it is also equal to the intersection of the domains of D plus and D minus. So what this lemma is basically telling us is that if we want to deal with some non-symmetric operator D, then there's basically two things we can do. We can either look at the real and imaginary parts, which are symmetric and therefore easier to deal with, or we can look at these operators D plus and D minus, which are also symmetric. So I'm going to do both. I'm going to provide a definition for the real and imaginary parts and one for D plus and D minus, and I'm going to show that they are in fact equivalent points of view. All right, so I want to give a definition of indefinite spectral triple, and so the idea is to get some kind of Lorentzian spectral triple. And I think at the moment there are probably more definitions about Lorentzian spectral triples in the literature than people working on it. So we have to somehow find a way to figure out what the right definition is. And there's this good old saying that a good definition should be the hypothesis of a theorem. So instead of asking what is the right definition, we should really ask what kind of theorems do we want to prove. So for me, I have two basic criteria that I want my definition to satisfy. And the first one is obvious. So the definition should include Lorentzian manifolds. That's the main goal. But if this is all we wanted, then it would be very easy to write down a definition. You just throw away all assumptions on your operator D, and then Lorentzian manifolds would satisfy that new definition. So we need something else, something to make sure that we keep both our feet on solid ground. And the other assumption, the other requirement, is that I want these operators D plus and D minus. These should give me actual spectral triple. So the usual definition of spectral triples. So I want to generalize the definition of spectral triples without losing touch of spectral triples. So that's the main goal. All right, so let me first write down the definition of a spectral triple, and then I'll modify it later. So I'll only focus on the even case. So it consists of an algebra, Hilbert space, and Dirac operator. So in the even case, I'm going to consider a Z2 graded Hilbert space, H, and have a star algebra representation phi from A to bounded operators, and these are even operators, so let me just write a plus there. And we have a closed odd operator, D, satisfying the following conditions. So in the indefinite case, I'm going to have 5 definitions. For the case of a spectral triple, the first 3 combine together by saying that D equals D star. We'll just summarize it like that for now. The fourth condition is commutators of D, let's say representation of the algebra, is bounded for all elements in the algebra. And the fifth condition is that the operator D has compact resolvent or locally compact resolvent. And I'm going to rewrite this slightly differently by saying that the inclusion of the domain of D into the Hilbert space is locally compact. And locally compact means that if we take the composition with the representation of an algebra element, so this is inclusion composed with pi a. This is assumed to be compact for all a. All right. So now I want to modify this definition to include Lorentzian manifolds. So let's have a look at what the Dirac operator of a Lorentzian manifold looks like. So consider a manifold M with metric G, even dimensional. It's going to be both time and space oriented. Lorentzian manifold. Such that following assumption holds. Yeah, there exists an orthogonal decomposition of the tangent bundle into a time-like part and a space-like part. So ET is a one-dimensional subbundle, and the Lorentzian metric is negative definite in my conventions on the time-like part. And this is then an n-1 dimension, rank n-1 subbundle, where the metric is positive definite. But I'm going to zoom a little bit. So that such a decomposition always exists. Given the Lorentzian metric, we always have one, but it's not highly non-unique. So this depends on a choice. And I'm going to soon assume there exists at least one such that the Wick-rotated metric, which you can define using this decomposition, as follows. If we have two tangent vectors P and W, then they uniquely decompose. And I'm going to define a new metric using the Lorentzian one. Where I change the sign of the time-like part, put a minus sign there. So this cancels the negative definite of the Lorentzian metric on the time-like part, and then you get a positive definite metric, which is going to give us a Riemannian metric. And the main assumption is that this Riemannian metric is complete. And then we can say two things. Let's see, so consider the canonical spectral triple for the Lorentzian case. So we look at smooth, compactly supported functions on M. We look at square integral sections. Canonically, this is a Krein space, as Niklas also explained. But you can turn it into a Hilbert space by using a fundamental symmetry. And this fundamental symmetry also depends on this decomposition. And then we have the Dirac operator, which is composition of Clifford multiplication corresponding to the Lorentzian metric, and the standard spin connection. And with this assumption, it follows that the real and imaginary parts of this Dirac operator are essentially self-adjoint. So it's proven by Helga Baum. And in fact, you can say the same thing about these operators, D plus and D minus. And you can say more than they are just self-adjoint, in fact. Yeah, they yield spectral triples. And this mainly follows from the observation that the principal symbol of d slash plus and minus is given by Clifford multiplication with respect to the Riemannian metric. So this will look something like gamma plus minus composed with the spin connection, where gamma plus minus v squared corresponds to the Riemannian metric. So this is symmetric. It's an elliptic differential operator. Yeah. Sorry? I don't think so, actually. No, no, no. So this is suitably nice Lorentzian manifolds. Yeah. 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 No, true. So Lorentzian manifolds. I mean, you have to avoid singularities to make this work, I think. Yeah. Okay, so now we can try and adapt our definition of spectral triple to make sure that something like this would fit into it. So I'm going to get rid of self-jointness because it isn't self-joint. The first definition is the same as I started with. So I want this to be a core, which will be true for differential operators because it contains smooth, compactly supported sections. And then the second is going to be this result. We observe it's true for the Lorentzian manifold, so we might as well assume it here. And then we have a third condition. So the third condition will be necessary to be able to prove that these operators d plus minus that I defined, that these should give spectral triples. And in the geometric case, the main assumptions that go into this proof is that you have nice symmetric elliptic differential operators, and the assumption that the Riemannian metric is complete. But so ideally I want to have those two same assumptions in the abstract case, but I haven't been able to make that work yet. So instead I'm going to put a stronger assumption basically, which is the assumption that if I look at the anti-commutator of the real and imaginary parts, then this must be relatively bounded by the real part of D. So this is bounded for all non-zero mu. And then to complete the rest, so I'm now also going to assume that D star has bounded commutators with the algebra. And for the last one, and this is basically why I rephrased it in terms of the inclusion of the domain instead of compactness of the resolvent. This is easy to generalize by saying that the intersection of the domain of D and D star must have compact inclusion in the Hilbert space. Okay, so the main observation that these two assumptions here and this was proven in a different context, but it's basically the same statement by Jens Kaat and Matthias Lesch. This implies that the operators D plus and D minus are self-adjoint on this domain. So we have requirement 2, namely that if I start with a non-symmetric operator D and I construct these operators D plus and D minus, then I get something self-adjoint. If we go back to the geometric case, then we kind of have a problem. Because in general, this is not going to be satisfied by Lorentzian manifolds. So if we look at this anti-commutator, then this is going to look something like this. So we get time-like derivatives of the space-like gamma matrices, as well as space-like derivatives of the time-like gamma matrices, and some other mostly lower order terms. And if you want this to be relatively bounded by the real part of D, so the real part of D contains all the space-like derivatives, then the only way to make that happen is to make sure that you get rid of all your time-like derivatives. So somehow it's only valid if this term cancels out. And it basically boils down to having to assume that this commutator is 0. And in general, this will not be true. This assumption basically means that your orthogonal decomposition here is parallel with respect to the Levi-Civita connection. And this is a reasonable restriction on your manifold. This is in general not true. So at the moment, I have a bit of a trade-off between the two requirements that I want. So if I want to be able to get spectral triples, then I, for now, have to assume this stronger condition, and then I exclude some Lorentzian manifolds. So it's still a work in progress to try and generalize this third condition and to get something without having to throw away other Lorentzian manifolds, but we'll see where that leads. Yeah, one attempt, sorry, yeah?
Just a question, how those conditions would be very specific to Lorentzian or arbitrary signature?
Arbitrary signature. So in particular, it includes all spectral triples. All Riemannian manifolds are also still in there. So it's not a switch from Riemannian to Lorentzian, it's really including both, yeah. And also pseudo-Riemannian and arbitrary time dimensions, yeah. But in particular, it's good to point out that if you just plug in that D is D star, then you just end up with the usual definition of a spectral triple. I'm sorry? Yeah, so in the Riemannian case, instead of this gamma 0, you would have the identity operator, which of course always commutes with the connection, yeah. So there's no restriction in the Riemannian case, no. Okay. So now I'm going to give my second definition, which works with these operators D plus and D minus. So I'm not sure if I mentioned the term yet, but I usually refer to D plus and D minus as being the Wick rotations of D. And in the classical case, this makes sense because the principal symbol of the Wick rotated Dirac operator is indeed the Wick rotated, the Clifford representation corresponding to the Wick rotated metric. Yeah, so there's a choice. You can rotate one way or the other way, and it doesn't really matter. Yeah. Yeah. So now I'm going to consider what I call a pair of spectral triples. So, in particular, these are spectral triples, two of them, HD1. So the usual definition of spectral triples, nothing indefinite about it. And with the additional assumptions that the two operators have the same domain. Both their sum and the difference are essentially self-adjoint on this domain. And third assumption, if you look at the difference between the squares, then we want this to be relatively bounded by the sum. Okay, so now the main theorem is that these two definitions are equivalent in a sense. So if AHD is an indefinite spectral triple, then by taking these Wick rotations, D plus and D minus, this is a pair of spectral triples. This is one way, but then we would like to be able to go back as well. So in order to go back, you write down what I mean with reverse Wick rotation. So given a pair of spectral triples with operators D1 and D2, I can define a new operator D by looking at their sum and taking I over 2 times their difference. And using this reverse Wick rotation, you can also go back. And I mean, the proof is not too difficult. So here the sum and the difference are precisely the real and imaginary parts. So that's the same assumption as up there. And this third formula is precisely requirement 3 up there, just rewritten in terms of different operators. And if you take the Wick rotation, then those operators are self-adjoint on this domain, which by assumption is compactly included, so they get compact resolvent automatically as well. Oh, sorry, yeah. This is bounded, yes, sorry. For all non-zero mu. Non-zero real mu. And I should point out that these constructions of Wick rotation and reverse Wick rotation are, of course, inverse to each other. So if you first Wick rotate and then reverse Wick rotate back, you get the original operator. And in fact, this is the main reason why I want to assume that the intersection of the domain of D and D star is a core for D, because if you reverse Wick rotate, then this is true by construction for the reverse Wick rotation. All right. So we have these two equivalent viewpoints of dealing with non-symmetric Dirac operators, basically. So it includes all spectral triples. It also includes all Lorentzian manifolds. But it's not only useful to deal with Lorentzian manifolds. It might be useful more generally. So for instance, if you look at the operator x plus dx, so multiplication by x and taking the derivative with respect to x as an unbounded operator on L to R, then we can also use this to construct an indefinite spectral triple. So this is obviously not self-adjoint. But we do get a spectral triple. And to make it even, I take 2 copies of this Hilbert space. And just to get the sign right, so this operator, of course, you should think of as being the annihilation operator for the harmonic oscillator, and its adjoint would then be the creation operator. So this is an indefinite spectral triple. And its Rick rotations are this form. And the other one is just swapped around. So this is also an example that where you construct a non-self-adjoint operator, and it does naturally fit into the definition of indefinite spectral triples. All right. So the next thing I want to do is construct another class of examples of indefinite spectral triples. And I would think of this class as examples as being foliations of a spacetime. So the idea is I'm going to start with a globally hyperbolic spacetime, which topologically decomposes as a product of a, say, a space-like surface sigma with the real line as the time parameter. And the metric is of the form, we have a family of metrics gt on sigma depending on time, and we have a simple metric on the real line as well, where n is the usual lapse function. And so this lapse function can depend both on the space and time coordinates. And we assume that each space-like slice sigma t, so this is manifold sigma with the metric gt. And again, we have here a completeness assumption. So we want this manifold to be complete. And then for all t, what we get is a spectral triple. So the functions on the space-like surface. Again, we have square interval spinors, where the spinor bundle is just a restriction of the spinor bundle on M. And you canonically get a Dirac operator, which depends on T, and which is constructed using the Riemannian metric GT. And This is then a spectral triple. And the idea now, what I want to do is sort of glue this family of spectral triples together to get an indefinite triple on the total manifold M. And the way I'm going to do this is as follows. So it's mostly inspired by something that Koen and Lesch did. They had a slightly different context, but so what they looked at is they have a family of operators on some Hilbert space. You can turn this into a Kasparov module by looking at the Hilbert module of functions on R with values in the Hilbert space. So this is a right C naught R module. And the operator D, if it behaves suitably well as a function of T, extends to a well-defined operator on this Hilbert module. So this represents a class unbounded Kasparov module, just the action of the complex numbers on the left and C naught R on the right. And what you can then do is take the internal Kasparov product with just the standard spectral triple over the real line. Again, there's a choice of sign here. So this is a spectral triple or a Kasparov module of a C naught R and C. And then if you construct this Kasparov product of these two classes, then you get something just in CC. So this is, this is representing a Kasparov class, CC, which is just the integers. And you can give a explicit construction of this. So, sorry. You now get a Hilbert space. And you get some product operator here. And so the main reason why Jens Kade and Matthias Lesch looked at this, basically they observed that this integer that you get in this K class, you can think of it as in two different ways. It's either the index of this product operator, or it's the spectral flow of this family of operators and gives the same number. But I want to use this in a different context. So I want to end up with a triple over M. Complete Riemannian manifold, yeah. Mm-hmm. Yeah, so you can, yeah, so if you take the restriction of the spinor bundle on M, then you maybe have two components of them. Yeah. No, I think I want to look at the restriction in order to get the same thing back. Okay, so I want to end up with a triple over M. So if I think of this as being the algebra, Hilbert space, and family of operators, I don't just want to have complex numbers here. But I want to have something like this. It's a function on R which take values in this algebra. And then, of course, I also get the same algebra still here. All right. So I need to say something about, I have enough time? Yeah, looks like it. I need to say something about what it means for this family. So I'm going to also put in an algebra here. And in fact, I'm going to allow the representation of this algebra to also depend on the time t. So I want to make sure that all these objects depending on t are well behaved. And I'm going to merge this into this definition. So if we have a map from R to bounded operators between two Hilbert spaces, and we say it has uniformly bounded weak derivatives if, so first of all, it must be weakly differentiable. And at each point t, this weak derivative must give me a bounded operator between h1 and h2. And I want the supremum over all t and r to still be finite. And this condition precisely ensures that the operator S dot on the corresponding Hilbert modules is well defined. Sorry? So I want that the map from T to ST psi, but this is in Hilbert space 1 and this is Hilbert space 2. This must be differentiable. Yeah, okay, not only this per se. No, you're right. But it's gonna come in later as well. Yeah, no. you can have weaker assumptions to make this well defined. Yeah. But at the very least, it is sufficient to make it well defined. So consider a family of spectral triples. So the Hilbert space is always the same. We have a family of operators and a family of representations of the same algebra, parameterized by the real line, such that there exists a Hilbert space W with a dense, continuous, locally compact embedding into the Hilbert space H. And I want the domain of the operators dt to be equivalent to the inclusion of this Hilbert space W, and in particular the graph norm corresponding to dt should be equivalent to the Hilbert space norm of W, and I want this uniformly. And third, these operators d and phi as a function of t, as well as the commutators. These should have uniformly bounded weak derivatives, as I just defined. So again, this is a sufficient condition for what I'm going to do. It might be able to be weakened. Right, so it means that not the inclusion itself is compact, but if I compose it with an element of the algebra, then this map is compact for any A in the algebra. Yeah. That's a equality, isomorphism, yeah. So basically this Hilbert space W can always be used as the domain of dt. And so the domain doesn't change as a function of t. That's the main message here, yeah. All right, so given such a family, we construct the same Hilbert module. This operator D. Let me just specify, by the way. So define a representation on this algebra. So let's say C naught R linear endomorphisms of C naught R H. And so with an element A in here, if I act on a psi in this Hilbert module, then if I evaluate it at a point t in R, then that definition is exactly what you would expect. You just put t's wherever you need to. So it's a representation at t of A evaluated at t acting on psi evaluated at t. And what we then get is that this Hilbert module with this operator is an odd unbounded Kasparov module. So for the algebras, C naught R A on the left and C naught R on the right. Okay. So now we want to move towards using this Kasparov module and then constructing the Kasparov product with a standard spectral triple on the real line in order to get a triple on the total manifold. So this product operator defined like this. So again, we have a doubling here because we move from an odd Kasparov module and an odd spectral triple to something even. And we get a 2 by 2 matrix looking like this. And then final result is, so say we have this algebra. So take 2 copies of this Hilbert space and then it was proven by Koen and Lesch that this, first of all, it's a spectral triple, and second, it represents the Kasparov product. So that's the Kasparov product of this Hilbert module and the standard spectral triple. So now I observe I had 2 choices for the sign in this standard spectral triple. And it's an easy observation that you have 2 operators here. And in fact, they give an even pair of spectral triples. And the main thing that you need to prove here is this, see, I erased it, this third condition in the even pair of spectral triples. So and this relies on this commutator being relatively bounded by D. But in fact, this condition you already need in order to make sure that you have a spectral triple representing the Kasparov product here. So again, Koen and Lesch have already proven this for me. And so it then follows that we have a pair of spectral triples. And then by the theorem I wrote down earlier, it immediately follows from 2 that in fact look at this triple. And then the operator looks like this. So this is the reverse Wick rotation of these 2 operators. This is then an indefinite spectral triple. All right, so this has been proven in the abstract setup, assuming that the family of spectral triples I started with is suitably nice in this sense. And I'm still working on what kind of conditions I need to put on the family of metrics up there of my space-like hypersurfaces in order to ensure that these abstract conditions are indeed satisfied. So that's work in progress, and we'll see how far it gets me. And I'll stop here, so thanks for your attention. Yeah. So I mean, it's more than just Lorentzian manifolds. Yeah. I mean, it's also Riemannian manifolds, first of all. But in addition to that, yeah, it's more than that. Yeah. Yeah. I mean, it's impossible to have a Lorentzian metric on one dimension, of course. So maybe. But yeah, it includes a lot more. Yeah. Yeah, I'm not sure which papers those are. No, sorry.
I'm not speaking about this. So maybe just raise the question. I mean, in this general statement or formalism or definition of what is indefinite, can you say something about the signature?
At the moment, no, not yet. No. Yeah, so the main example I wrote down the harmonic oscillator, but yeah, otherwise I'm not sure. Not sure. Okay, worth having a look at, yeah.